Hello, so this is my resource on the hyperboloid of revolution. For it, I'm going to be concentrating on asymptotes and how they work off the key principle of if a line is parallel to the xy line in one view, it will be a true length in the other. And I'm going to use SolidWorks for it because it's a great tool of way of making something that is a 2D drawing, like here, into a 3D shape. And I like doing that because students a lot of the time, like I did myself in school, struggle to visualize what a 2D drawing looked like in 3D. And especially for something like this, where your asymptote is a straight line that is supposed to touch the surface of a curved surface from start to finish. So hopefully now this resource helps kind of ease that a bit. So here I have the hyperboloid of revolution that I had from the drawing, and we're just gonna show visually how that asymptote works and how it is touching the surface the whole way, and then get into why that rule key principle works. So here I have the hyperboloid of revolution. I have the asymptote and it's tangential to the throat circle and everything, and um, then when we rotate it up, we can see that it looks like it should. And what SolidWorks is really good at is, like I said before, making a 2D drawing into a 3D shape, and we can just rotate it around to see that that asymptote from start to finish is actually on the surface the whole way. So like when you rotate it around, it will rotate around with it. So there is just kind of a visual aid for some whatever students are kind of struggling to see just what the asymptote is, how it is explained in the book can sometimes be a bit misleading considering they don't have enough pictures in it. For example, if I open it up here, like this is what they talk about in the asymptote. There's no kind of 3D models like this to help students visualize it. Um, and to get into the nitty gritty of like why that works, so this hyperboloid of revolution is a doubly ruled surface. So like if I was to pick this middle point, the doubly ruled surface means that there's two straight lines that will pass through it, and that's how asymptotes work. So for every asymptote you have here, you have two, or for every asymptote I have in plan that looks like this, you have two actual ones. So when I rotate this up, like for that one asymptote in plan, there's actually two actual asymptotes because there'll be another one going from left to right instead of, or from bottom left to top right instead of this top left to bottom right. Um, so that would be your two lines. So if I was to pick that middle point just for argument's sake, they would be the two straight lines that would be able to be drawn through that point on the surface. And so then to move on to the principle of this being parallel to the XY line in one view and being a true length in the other, I'm going to show that visually. So how we know this is a true length in elevation when it is parallel in plan, I'm going to use a tool in SolidWorks. I'm going to insert a plane. So to go back to junior cert tech graphics, we know from orthographic projection that you can't see the true length of something or the true shape unless the spectator is looking straight in front of it or straight at it. And to show that we are looking straight at this line and that it is a true length, I'm going to insert a viewing plane on it. So if I click the um, first reference, is just the plane, and the second reference to be this. Oh, um, there it is there. So we can see that I have this asymptote coming from the top to bottom, and the viewing plane is on, like the viewing plane is on it. So you can see the viewing plane is cutting the hyperboloid of revolution in the same place that the asymptote is cutting or going along it. So for every one point, which is the center point, you are getting two asymptotes. So this line here and that line there, which is our actual asymptote. So that kind of proves that we are looking straight at this line. It is a true line. And how that works is it's very simple. So for us to get it, be looking straight at it, it needs to be parallel. And to prove that it needs to be parallel, we'll just change the orientation. So this is the exact same asymptote, just different orientation. So we're now looking at it here. And when I rotate that up to elevation, it's completely different. It's just a straight line from top to bottom. Now, you might get confused and say, oh, well, that's the true length. But when I rotate it around, this line is obviously longer, like it travels a further distance. The original one was just straight up. And if I was to just sketch here. So the original one in the last view was just straight up. But obviously it cannot be the true length because that length distance is shorter. As you can see, that's the same distance. It's that much shorter than the true length. And that's kind of how we justify saying you need to or that's how when you need to have a parallel line in one view to the XY line will be a true length in the other. And that's just kind of a visual representation of how that works and why it works. Because if you go around messing with views, you're not going to get the actual true length because you're not looking straight at it.